In our chapter 25, we look at radical chemistry. Radical chemistry is a big kind of mess, and all sorts of different things can happen, and it's actually kind of neat to go through and evaluate. Unfortunately, it plays a relatively minor role, so we won't talk about it a whole lot. Its primary functionality is really going after the alkane functional group, which, if we remember something about the characteristics, our alkanes are made up of all nonpolar bonds, which means virtually no reactivity. So how does a radical go through to work? Well, we got examples of radicals on the far right, and the characteristic they all share is they all have a single unpaired electron. It is that unpaired electron that drives their reactivity. And so what they're trying to do is somehow neutralize that electron by pairing it up with some other single electron. Okay, so as far as their reactivity, they are roughly equivalent to a cation. So they're unstable because they have an unpaired electron. And they react with the most available electrons relatively quickly. And so our most available electrons are going to be found typically on the outside of our structures. And so that's where we're going to need to keep our focus. To go through and start all radical reactions, you're going to start with an initiation. We need the formation of a radical, and this is going to happen through homolytic bond cleavage, which we talked about when we looked at our redox reactions. We identify the bond. Okay, in this case, it is the one between two very electronegative elements, and that bond is going to homolytically cleave, meaning the electrons in that bond will go to their parent atom. And that is because both atoms are very, very electronegative, so the electrons will split to their parent atoms. And this ends up generating your radical. And in this case, or these two cases, you end up with two radicals. Okay? This can be done with heat in the case of a really, really weak bond, like the oxygen-oxygen bond, or sometimes light in the case of Br2. Once initiated, these radicals can then go through and react with other structures in a variety of fashion in what is known as typically a propagation reaction. So if we go through and look at our bromine radical reacting with an alkane, there is the potential that our single electron can come through and take, I drew that pretty horribly, and can take our electron and we form the primary radical. The other possibility, if we went through and had our bromine radical react with the other hydrogen, we could form a secondary radical. Okay, and so one of the things that's going to contribute here is that, well, which of those products is more likely to form? Okay, well, in this case, the more likely product to form is the secondary radical because it is more stable. And so we have to look at some kind of energetics behind this. Once we have that radical, or now a carbon radical, that carbon radical can react with other species. Okay? Odds are that we would probably encounter more bromine, so our radical can go through and do more radical reactions. Notice in each of these cases, what we end up forming in all cases is a radical and a neutral species. So we start with a radical, we end with a radical, we're looking at a propagation reaction. As far as deciding what product is favored, a lot of this comes down to the reactivity of, number one, the bromine radical to initiate this whole process. So reactive, or how reactive. And then number two, the reactivity of the possible products. When we look at bromine as our radical, while it is reactive, because it is large, it can stabilize that loss of an electron relatively well, and so the bromine is kind of, in the grand scheme of seeing things, less reactive, which means it can be very selective over what it's going to react with. If it can kind of chill and stabilize that, it wants to make sure that the product it produces is the most stable possible product that it can get, and you're going to end up seeing a secondary radical come out of this as opposed to the primary. And that's because the secondary radical is more stable than the primary. Okay? And our primary is less stable. So when it comes to bromine reactions, we tend to see the secondary radical intermediates being formed. And that largely has to do with stability. If we continue to let our reaction run, we still have these radicals free floating around, and we can eventually find that those radicals will encounter each other, and we do what's known as a termination, or the loss of a radical. So we've got a couple examples here. The radicals meet in free space, and we end up forming a bond between the carbon and the bromine. One of the things that I didn't address already as we went through and looked at this is that when we draw our radical mechanisms, you may notice that we're using a single-headed arrow, but then also our electrons are going into this kind of empty space. Well, that's the empty space of where the bond is forming. We can't do it like we would a normal heterolytic 2-electron arrow pushing because, well, we don't have 2 electrons to move. We only have 1. So we end up doing kind of this weird in-between system with our mechanism. One of the termination steps that you may notice, okay, that kind of third one, is an interesting one. We're having 2 of our alkane radicals come together. Still perfectly allowed, and it is possible to happen in our reaction. One of the things that comes up when we're looking at our radical reactions is possible versus probable. There's a lot of things possible, but we can control which of those possibilities happens more frequently by changing concentrations of our individual species, which, yes, makes radicals a bit of a beast to go through and process. There are other circumstances where we just let the radicals run for however long to make larger and larger structures, and then eventually we may say, okay, well, I want to kill it. Okay, we can kill the reaction by adding in something known as a scavenger, and what that scavenger will do is react with the radical and terminate its activity. Once the radical's been killed, our reactivity is kind of done. Okay, so our termination are now the loss of radicals. So utility. If I wanted to go through and do this synthesis, okay, you might notice that we have a double bond forming. Okay, well, to make a double bond, I need to do an elimination reaction. Okay, but in the elimination reaction, what are things that I need? Well, I could get away with using a base. Okay, that could be useful. But even with that, I need a leaving group. If we go back to the starting material that I'm given, do I have a leaving group? No, there's no leaving group. Okay, there's no reactivity at all in this compound. So I need to initiate it and get it reactive. That's where the radicals can come in. I can react this with bromine under radical conditions, and what will end up happening is I will do a substitution, a radical substitution. Okay? And that radical substitution is going to substitute hydrogen for bromine, where I would generate the most stable radical intermediate, which in this case would be the tertiary location. So do I have a hydrogen at the, whoops, I should draw it up on the top one. Do I have a hydrogen at the tertiary position? Absolutely. That means I can go through and form the radical at that position, and I can then do my bromine substitution. Now that I have a leaving group, I could initiate this with a good strong base. Okay. That base could come in, remove electrons from a hydrogen, and we end up doing our elimination to get us our final product. Okay, so our big utility of our radical reactions is to get our alkanes in a position where they can react. Okay, so our primary reaction is a radical substitution. We're using elemental bromine, potentially with some kind of initiator. Okay, that initiator is sometimes shown as light, okay, or sometimes heat. Okay. Light is a huge one. If you see light, you should immediately be thinking, oh crap, this is radicals. And if you see just an alkane that's somehow becoming something else, you should immediately be thinking radicals. Okay, so these are our big chemistries. When we go through to think about which type of halogen to react, bromine's really the only synthetically useful one because it is selective. both fluorine and chlorine are non-selective. Fluorine is so fluorine with an F is so non-selective that if we try to do an alkane fluorine radical substitution, it explodes. Literally explodes. That's not very useful. Okay. Chlorine, on the other hand, is still pretty reactive, just not quite as reactive as fluorine. This means that chlorine will react with any and all hydrogens it has access to. Well, if we look at the structure we're starting with, there's lots of hydrogens, which means there's lots of chlorination products. Bromine reacts even slower still, so because it is a slower reaction, it will then favor the most thermodynamically stable product, as opposed to just getting a kinetic product right out of the gate. Okay. So our reagents, again, bromine, light, or H-nu is sometimes what you'll see. That's the selective one. That is really kind of your primary be-all reaction. It's hard to really say anything else about any of the others. You may see chlorine pop up. Okay? If chlorine pops up, it's popping up as a non-selective reagent, and they're really just testing your understanding that it is non-selective. The hydrogens can go anywhere. So for example, if we drew out a potential product, we could end up with putting the chlorine there. Okay? Or really any place that there were hydrogens. And again, we go for hydrogens because they're the most readily available. Okay. Fluorine is way too reactive. It releases so much energy that we get massive explosions. Iodine is also highly selective, just like bromine. However, iodine reacts stupidly slowly, meaning that if we tried to do an iodine radical substitution, we'd be waiting days, if not weeks. Okay, so it's just not synthetically useful. An energy diagram to get us an idea of what's going on with this. When we look at the reactivity of our starting materials, the bromine radical is relatively stable, which means it kind of drops the energy of our reactants. Okay. Chlorine, on the other hand, as a radical, not very stable, so it ups the energy of the reactants. And this is kind of an interesting energy diagram, because if we go through and look at it, the thing that's not changing is actually the energy of our products. The products are what's staying constant in this comparison. What we're looking at is the energy of our reactants. Chlorine is so more reactive as a radical that the reaction becomes exothermic. Exothermic, we go whichever one happens fastest, and we get slightly different products coming out of this. Okay. If we go through and look at the bromination reaction, the bromine radical is so much more stable that we get an endothermic reaction. We end up seeing a large preference for the more stable radical coming out of it. Okay. So synthesis, use bromine. Stereochemistry. What kind of stereochemistry might we expect out of this reaction? Well, let's kind of break down our mechanism, which we haven't done yet. Bromine, being selective, is going to go for one of our more substituted hydrogens. So we'll take a single electron. Let's use a different color. We have to explain where the other electron went. So we would end up with our radical and bromine radical floating around. Okay. Theoretically, these two would never encounter each other, and that these are more than likely going to encounter other molecules. Okay. So let's go through and predict that. More than likely, we would expect that top one to encounter another molecule of bromine. So we might expect this kind of result, which would get us to our final product with the bromine attached and a bromine radical. The other one, more than likely, would encounter more just alkane floating around. and we would end up forming more of that carbon radical, which could then react with more bromine. Okay, so let's clean this up a little bit and just kind of focus on the part that's relevant, looking at our stereochemistry. If we look at our final product, do we have a stereocenter to worry about? Fortunately, yes. There's our stereocenter. Okay, well, we go back to our starting material. Was that carbon a stereocenter to begin with? Okay, no, it wasn't. It was achiral. So that means somehow or another, when I look at the products, okay, whatever those products must be, the total products, it's important to remember total, must be achiral as well. So what's going on here? How did we lose chirality in that product even though it's achiral? Okay, well, that comes into play because our radical intermediate can react with our bromine either above or below, because remember, it equates to a carbocation, which means when we look at the product, I could either have that bromine wedged coming at you, or I could have ended up with the product with the bromine dashed going away. Both are equally likely, which means we end up with an achiral product. So no optical activity, even though there is a stereocenter in the molecule. Something that's important to remember when we look at our radicals. Okay? So this usually means we're looking at racemic products. What happens if we now change our structure? So in this case, you'll notice we have an alkene and alkanes. And if we went through and reacted this bromine as we might have anticipated, say if we ignored the light, hopefully what you would be able to get to would be this product, where we have the addition of bromine. Okay? But what happens if we go through and actually have light being present? Well, if light is present, then we're doing a radical reaction. Okay? Well, in the presence of bromine, that means no heterolytic bond cleavage of our alkene, and what we need to focus on is forming the most stable radical. So you need to pull off hydrogens and identify your most stable position. I really hate to do this, but at this stage in the game, we just have to jump straight to the answer. Our answer is going to be forming that radical at one of the positions next to the double bond. That position, which I'll now call our purple radical, is allylic. Okay? That allylic position has resonance stabilization. That resonance stabilization is what facilitates the formation, okay, of our radicals, which then leads us to the final product of putting our bromine at one of those positions, and in this case ultimately giving us two different products. Okay, so the double bond introduces an issue within our radical reactions because we actually form a more stable radical by doing allylic reactivity. So we have to be very, very, very careful with the context of bromine. Is bromine being added by itself, in which case you should see it as an addition reagent because it acts as an electrophile, or is it being added in the presence of light, in which case our bromine is acting as a radical initiator? Okay. Two drastically different products, and it's all going to center on, do you see the presence of light? If you see light, you should be thinking radical products. Okay. One of the kind of issues that pops up with this is that if bromine is present in a high concentration, we might end up getting a mixture of products. We might get the addition product and, oh shoot, now I gotta draw them all out. Our addition product as well as the radical substitution product. Okay, well, if we don't want both, we're going to have to limit one of those reactions happening in preference or deference to the other one. The easiest way to do that is to limit the presence of Br2, because Br2 is what is potentially taking us to our addition product. So to limit its presence, we can control it a little bit, and that's where we can use the species N-bromosuccinimide. Okay. NBS still generates that very weak, polar bond between the nitrogen and the bromine. Okay. NBS will react with other NBS molecules to form our succinimide molecule, as well as very small amounts of Br2. In the presence of very small amounts of Br2, we will end up forming the radical, and we tend to prefer the allylic substitution as opposed to the addition. Okay. For those of you in lab, I'm sorry, when you see NBS, you should be thinking radical substitution, not addition. If you got questions about that, you can ask in class. So, radical substitution reagents, Br2 and light. Bromine will substitute for hydrogen at the most substituted position. Cl2 and light, chlorine will substitute hydrogens at all positions. That sucks. We tend to avoid it. NBS and light or heat, bromine substitutes a hydrogen at the allylic or benzylic position. Remember, both of them have similar chemistry. So it's again another big summary here. We were kind of pushing and hoping that Br2 and light was the only thing we had to worry about. Unfortunately, the next big reagent for synthesis, NBS. Okay. Either way, NBS and Br2 are doing the same thing. They're just slightly different versions of that reagent. Okay. So that covers our substitutions. Well, can we go through and do radical additions? Okay, yes, we can. Though the radical addition is going to involve slightly different reagents. Number one, we're going to end up with peroxy initiators, okay, which you may remember from the MCPBA, or our epoxide formation. In the peroxy initiator issue, we have a perfectly symmetric structure, okay, of our peroxy species. That means when that bond cleaves, it cleaves perfectly to give us our radicals, but two of them. Those radicals can then go through and react with other things present. So typically where you will see this is in the presence of an alkene and HBr. Okay? Between those two, the one that is typically present in higher concentration is our HBr. Okay? That becomes relevant because that's going to determine what our radical reacts with first. So it's going to react first with the HBr. Okay. What does this then generate? Well, this gets us our now neutralized oxygen radical, and it generates a bromine radical. Okay. Well, now what's the bromine radical most likely to encounter? Excuse me. More than likely it'll encounter more HBr. Okay, so don't write this down, but I'll show you. If it encounters HBr, what happens? Well, we end up forming HBr and bromine radical. So nothing happens, it's a wash. So that will continue to happen until it encounters something else in solution. Okay, well, there's two something else's in solution at this point. There's the acid form and our alkene. Okay, between those two, which one is more likely to react? Okay, well, this again comes back to concentrations. Okay, our radical initiator is present in very low concentrations, just enough to get the reaction started. Well, if this is in low concentrations, what does that mean about the next species? Well, it's also in low concentrations, which then means our acid form is also in low concentrations. Well, if it's low concentrations, odds are doesn't react. That then puts us in the situation where our bromine radical will react with our alkene. So now the question is, what does it react with preferentially? We do still have the possibility of it reacting with the hydrogen to form a allylic radical. And while that is a possibility, there is another potential site of reactivity. That is directly with the pi bond. Okay, and this again comes from kind of concentration gradients that we might expect within our solutions. So what happens? The bromine radical shares an electron, our double bond shares an electron. Okay. This then goes through to produce one of two possible answers. One, we put the bromine at the secondary position, or one, we put the bromine at the primary position. Okay. That is going to be dependent on what happens to the other electron in our reactive double bond. Remember, when we're looking at our radicals, we're almost always doing three arrows. Okay. Our radical arrow representing the pi bond, we only moved one electron. The other electron is also included. So we end up with two possible products, one where we form a primary radical, one where we form a secondary radical. Which of those two structures is more stable? Okay. Well, the more stable one we can equate back to cations. Which of our cations is more stable, primary or secondary? Secondary. Good answer. This sets us up with now a new radical. What is this new radical most likely to encounter? Well, just like with the bromine radical that we had before, and the peroxy radical that we had even before that, the most likely thing it encounters is HBr. So now what happens? The bromine shares an electron. We take an electron from the HBr bond, okay, to generate our final product, with our hydrogen now being added to the structure and our bromine radical, which can now go out and continue to propagate the reaction. Okay? So it's kind of an interesting result. So if we clear all that now, so you either need to pause if you want to keep looking at it, or just let it go. If we look at the end result, what we end up with is doing a radical addition where we have added bromine and hydrogen across the double bond. Okay? As an extra interesting feature, what happens if we had tried the same reaction with just adding HBr? Okay, well, if we just add HBr, double bond reacts, we generate the more stable carbocation. The more stable carbocation is the secondary position, and we would end up with a product where the bromine is at the secondary position. So our radical addition ends up dumping the hydrogen and the bromine at opposite locations of what we would expect or have predicted using, heaven forbid we use his name, Markovnikov. Okay? This is again one of those reasons why Markovnikov as a rule is dumb. Depending on the conditions you're running under, you will see your hydrogen atom go to different locations depending on if it's acting as a radical or if it's acting as H+. We need to be very, very careful with assigning what's happening within those. Okay? So HBr now becomes another tricky reagent. If you see HBr in the presence of some kind of radical condition, that radical condition being an oxygen-oxygen bond, okay, then you need to be putting the hydrogen and the bromine in the opposite locations of where you would think to put them, or where you would want to put them based on their heterolytic bond cleavage. Okay, which is nasty, but that's the way it works. Okay? And there's some nice kind of steps drawing it all out. So, if we look at our radical additions, we now have two ways to react, or radical reactions. We have two ways to react around an alkene. Number one, with NBS, we can go through, that's a horrible starting material to pick, we can do a radical substitution where we put the bromine at an allylic position. So I picked one of your possible products. The other one would have been putting the bromine at the other position. Okay, so both of those are possible products. Or I could have gone through and done an addition reaction around my alkene as opposed to a substitution, and that ends up resulting in pretty much the opposite of what we would expect. Okay, notice again, there's that oxygen-oxygen bond. Okay, I don't really care what's out there in those R groups. Those could be virtually anything as long as I have that oxygen-oxygen bond. Okay, that is my radical initiator. I have a hard time saying, well, it's opposite of what I would predict. So what I would do is go through and just say, okay, this is radical, and radical equals opposite. So I would go back to my double bond and say it probably makes sense to put the negative charge here and the positive here, which would mean that I would expect to put the bromine here and the hydrogen here, but it's heterolytic. Radicals do the opposite of the heterolytic reaction. That means when I draw out my product, I need to put them in the opposite locations. And the hydrogen I can imply. Okay, lovely, big mess. I'm sure you love it. That's the way it works. Okay, sometimes we just have to deal with what we've got. Okay, the Birch reduction. Sodium metal can act as a reducing agent. We already saw this one briefly in class. You go through a radical mechanism primarily because, well, sodium is a radical. Sodium metal, by definition, is a radical. It only has one unpaired electron, so it has to act as a radical. And so we could go through and evaluate the rest of that. The other option is looking at it react with a aromatic ring. Okay, here's the big mechanism of it. You can go through and look at it and evaluate it if you want. It is not critical for this semester. We will talk about it again for sure in second semester. If you don't have to take second semester, you don't got to worry about it. If you do, you will see this again. This just happens to be the mechanism. For those of you that don't like curved arrows, maybe someone with the initial CB, sorry, this one sucks. You got a ton of curved arrows bouncing through this one because you're looking at resonance and other things like that. You just kind of have to deal with it. Okay. If you want to challenge yourself to understand something about predicting what goes on, what would we expect the products of these two reactions to be? This is kind of a way out there left field challenge. You don't want to do the challenge, don't worry about it. If you want to do it, talk to me and we'll move from there. Okay? So I'll just pretend you didn't see those answers. So our big reaction summary is right here. If you have alkanes under radical conditions, bromine is your big key. Bromine and light. Okay? And that's going to do a substitution of hydrogen for our bromine. So we're losing that hydrogen for our bromine to get us now a reactive structure. Okay? Chlorine, on the other hand, is a crappy reagent to use because you end up with every possible freaking hydrogen substitution under the sun. Okay? Not a particularly fun reagent to use, not typically a good idea. For those of you that think I throw all sorts of crazy things at you, there are other classes that talk about the mathematics behind all that. You're welcome. I didn't give you that. When it comes to alkenes get tricky because we have our standard addition pathway, which we talked about earlier in the week, and then we have our radical reactions with our alkenes. We have a radical substitution, and we have a radical addition. Okay. Unfortunately, you're responsible for these. We'll do one more kind of discussion on radicals on Monday as we wrap up our redox slides and then hopefully get into just strict review. I'm pretty sure that's our last slide. There it is. Thanks for listening. Talk to you Monday.